This lesson is all about the law of cosines. The last two cases of oblique triangles we will learn how to solve are the SAS and the SSS cases. Thankfully, neither of which result in ambiguous cases. It is possible, however, that in the case of SSS, that is when we have three side lengths of the triangle known but no angles, that a triangle is not formed. The one requirement that must be met is that the sum of the two shorter sides of the triangle must be longer than the longest side. This is known as the triangle inequality, where a plus b must be greater than c. So for instance, if I have the base of a triangle, the longest side that is, 10 centimeters, and I have two side lengths where one is 2 centimeters and the other one is 3 centimeters, no matter what I do, I can't arrange this in order to make a triangle, because the two shorter sides of the triangle aren't longer than the longest side of the triangle when added together. Similarly, if I have a side of 10 centimeters where I'll leave this side over here as 3 centimeters, and say for instance this side is 9 centimeters. Now 9 plus 3 is 12, which is greater than 10. That would form a triangle. The law of cosines is effectively a generalization of the Pythagorean theorem that works for acute or oblique triangles. And when you see the formula for it, you'll understand as to what I am referring to here. So for instance, the law of cosines, when applied, it works for oblique or acute triangles. I'm just going to draw this in as an acute triangle. Notice how the side length A, for instance, has angle A opposite. B is the same situation as well as C. In this case, A squared is equal to B squared plus C squared, which is very similar to the Pythagorean theorem, minus 2bc cosine A. This last little part, the minus 2bc cosine A, it actually just disappears. It becomes 0 in the Pythagorean theorem. But when you have, that is when you have an angle that's 90 degrees. But when you have an angle of any other measure, you have this term, and you can basically use the Pythagorean theorem as long as you take into account this last piece. What else is nice about this is that it doesn't really matter what side of the triangles you're working with. You can just make sure that whatever side measure you're solving for over here, that you have the angle measure that's opposite that side that you're doing the cosine of here. And then these two letters always match these two letters. So you don't really necessarily need to memorize all three of these. Just memorize the form of them and you can apply it to any triangle. So the triangle that I'm referring to is the triangle here that is oblique. And I've split this up into two separate triangles that are right triangles in a similar fashion that I did with the proof of the law of sines. As we break things down into simpler parts and apply the knowledge that we already know in order to solve for new ideas. So what I'm going to do is I'm going to do some labeling. First off, the height of this triangle is k, the y value of this point. So h is the x value of that coordinate, and k is going to be the height. So I'm going to put that in. And I'm also going to label this angle right here as angle A, because it's the angle that's opposite side A. Working with 90-degree triangles, one thing that I can deduce is that h squared plus k squared is equal to b squared. So you should be able to see in the figure that h, k, and b make up a right triangle where b is the hypotenuse. So I'm just applying the Pythagorean theorem to that. And on the other side, I could say a squared is equal to k squared plus c minus h quantity squared. So why can I say that? Let's see. So the triangle that I'm working with, first off, is this triangle right here. And it is a right triangle. I know that this side is a and this side is k, but the bottom, what is that? Well, if this total distance from here to here is c, and this distance from here to here is h, then this remaining distance right here is c minus h. So that's why I have a squared is equal to k squared plus the quantity c minus h squared. Now, taking this first equation and just rearranging terms in it, I can say k squared is equal to b squared minus h squared. I'm just moving the h over. And working with the second equation, I can rearrange it and write it as a squared minus the quantity c minus h quantity squared equals k squared. Now, between those two, I have two different expressions that are solved for the quantity k squared. That means I can set both of those expressions equal to one another. So I can say b squared minus h squared is equal to a squared minus c minus h quantity squared. Since they're both equal to k squared, they're both equal to each other. And now I can just work with that algebraically. One thing I definitely notice is I could FOIL out the c minus h quantity squared. So that's where I'll begin. So I would have b squared minus h squared equals a squared minus c squared minus 2ch plus h squared. And then I have a negative that I could distribute. So b squared minus h squared equals a squared minus c squared plus 2ch minus h squared. Which is interesting. I have a term that is minus h squared on each side of the equation. If I add h squared to both sides of the equation, it's going to cancel both of those out. Which means I have b squared equals a squared minus c squared plus 2ch. Which is very similar to the form of the Law of Cosines, but I'm going to move the c squared plus 2ch to the other side. So I would effectively have b squared plus c squared minus 2ch equals a squared. All right, so hold that thought. So right now I have a squared equals b squared plus c squared minus 2ch. Okay, which is almost there. I'm almost done. The only thing that's left to do is just figure out what h is, because in how we've expressed the law of cosines, we haven't left anything in terms of h. We've solved it. And I think we can do that pretty easily. We can figure out what h is. So h is this distance along the base of this triangle right here. So let's see what we can do about solving for it. So using that right triangle, and I'll draw it in green so you know which one I'm referring to. I'm referring to this triangle right here. All right, I know that this angle measure is a, the base is h, the height is k, and this length is b. Okay, so with all of that, I'm going to say the cosine of angle A is equal to, so cosine is the adjacent over the hypotenuse, so it's h divided by b, which allows me to solve for h. All I have to do is multiply both sides by b. So b cosine A is equal to h. Now I'm going to take this, what I've just learned, and plug it in right there. So let me not take it off screen there. Okay, so now I have a squared equals b squared plus c squared minus 2c, and then h is going to get replaced with b cosine A, or finally a squared equals b squared plus c squared minus 2bc cosine angle A. And there we have the law of cosines. So again, it's all just based in right triangle trigonometry. So let's try some examples. Let's try an example. Solve the triangle with the following characteristics. Angle A measures 48.4 degrees. Side B is 6.94 meters. And side C is 12.21 meters. And I went ahead and drew a triangle. And if you'll notice, I have angle A opposite side A, angle B opposite side B, angle C opposite side C. And that's just to keep the information organized correctly. It really doesn't matter how you scale this triangle. It's just to have a place to put the information that's given. So the information that's given is angle A measures 48.4 degrees. So I'm going to go ahead and write that in. Side B is 6.94 meters. And side C is 12.21 meters. Okay, now in order to solve for the remaining sides, what we have to note is how the known sides and the known angles relate to each other. So I have one side, and then an angle measure, and then another side right in a row here. So this is the side angle side case. And with the side angle side case, what we have to do is start off by solving this using the law of cosines. And the law of cosines, I showed you 3 different ways of expressing it. But effectively, the way I go about thinking this is the law of cosines is you start with the Pythagorean identity, and the side measure that you put by itself is going to be opposite the known angle, if you happen to know an angle. All right, in this case we do. So I'm going to write this as a squared equals b squared plus c squared. I'll fill in what side B and side C are in just a second. I'm just going to write up a formula here first. So this is basically the Pythagorean identity, but notice I didn't put c squared on its own. C was always the hypotenuse in a 90-degree triangle, and that always had to be by itself. But we don't have a 90-degree angle here, so that doesn't really work. What we do is just whatever's opposite the angle that's known or the angle that we want to find out. That's what goes by itself. And then the other 2 sides go together. Then it's minus 2 times b times c, the 2 sides that are already on this side of the equation, times the cosine of the angle in between them. So times the cosine of angle A in this case. Alright, so plugging into this formula, the known information, I will have a squared equals, alright, side B is 6.94. So it'll be 6.94 squared plus side C, which is 12.21, so 12.21 squared, minus 2 times 6.94 times 12.21 times the cosine of the angle measure between those, which is 48.4 degrees. I'm just about out of space, but I made it. Okay, now I'm going to get the calculator out and first solve for what a squared is. Alright, so here's the calculator. And let me move it over here to where I can see my equation. That's better. Alright, so it's 6.94 squared plus 12.21 squared minus 2 times 6.94 times 12.21 times the cosine of 48.4, and before I hit enter, I'm going to check my mode settings real quick and just verify that I'm in degree mode. And since degree is the checked box here, I'm fine. Alright, and we'll hit enter. And that's going to give me approximately, I'll tell you what I do. I'll write, this is approximately 84.73, although I'm not going to use 84.73. I'm just going on the calculator and I'm going to hit second square root. So if you hit the x squared key with the second, you'll get a square root. And then I'm going to hit second and the negative, which gives me the word ANS, standing for answer. So it's going to give me the square root of the previous answer. So this way, without doing rounding, I will have the most accurate answer I can get. You definitely want to avoid rounding until your final result. Alright, so that gives me A as about 9.20 meters. Alright, let me move my calculator back out of the way. That's good. And now what we have is side A, which is about 9.20 meters. Okay, and I wrote that in blue. I wrote the given information in green, just because if you can solve a triangle without using anything that you solved for already, just using given information, that's the way you should go about it. It's not always possible when you have to use the law of sines and law of cosines. You should avoid it if you can, but if you can't, that's just do the best you can. Now, I still need to figure out what angle B and angle C are. Alright, so to get angle B, I think what I'll do is I'll switch and use the law of sines next. So let me scroll down a bit so I have some space to write. So what I can say is the sine of angle B divided by the side opposite that, which is 6.94. That's going to be, now in this case I don't really have any way of avoiding using the 9.20. I have to use a known angle for the law of sines. So sine of 48.4 degrees divided by 9.20. Alright, so solving for this, let's see what happens. I would start off multiplying both sides by the 6.94. So it cancels out on the left-hand side of the equation, and I just have the sine of B, and that's going to be 6.94 times the sine of 48.4 degrees divided by 9.20. And let's get the calculator for that. So that's going to be 6.94 sine of 48.4 degrees divided by 9.2, so 0.564. So the sine of angle B, let me be more precise. It doesn't really make a lot of difference if you do this or not, but it's approximately 0.564. And then if I take the arc sine, I will reveal what angle B actually is. Okay, so I want to take second and sine, which gives me the arc sine function, and then second and answer, and that way I don't have to type in all those decimals to make sure I get the most accurate result. So 34.3 degrees is what we'll go with, because that original angle was to the first decimal, so I'll solve all the remaining angles to the first decimal as well. So this here is 34.3 degrees. All right, there, now there's a decimal. Okay, now the last angle measure. I could opt to solve for it, but since it's the last angle measure out of three angles in the triangle, I can actually determine angle C by taking the total of the angle measures should be 180 degrees. If I subtract the two known angles now, then that will give me the measure of angle C. So let me move this over just a bit and we'll figure out what that is. So 180 minus 48.4 minus 34.3, so 97.3 degrees. So this last angle measure is 97.3 degrees. And once we have all of the angles and the missing angles and the missing sides solved for, we have solved the entire triangle. So we are all done at this point. Next up, solve the triangle with the following characteristics. So side A in this case is 9.8 yards. Side B is 12.2 yards. And side C is 18.5 yards. Now, we don't know any of the angle measures between, so we would have to use the law of cosines in order to solve, because in order to use the law of sines, you have to know at least one of the angle measures so that you can, or at least one angle measure and the side opposite that. So in this case, we have to use law of cosines. To do that, we would say, for instance, 9.8 squared is equal to 12.2 squared plus 18.5 squared. That part's easy enough. It's just the Pythagorean theorem. But then you have to subtract 2 times the sides that you've put on that the 12.2 and the 18.5, so the numbers that are on the right-hand side of the equation, times the cosine of the angle opposite the 9.8, so the cosine of angle A. Now, we will need to do some work with the calculator, so let me pull it up, and I'll bring it over here because all right, So the first thing I'm going to do is figure out what 9.8 squared is and then subtract 12.2 squared and 18.5 squared. So I'm going to bring those terms over. So I'm going to do 9.8 squared minus 12.2 squared minus 18.5 squared. So that gives me negative 395.05 equals, then I'm going to do 2 times 12.2 times 18.5. So that's 451.4, so negative 451.4 cosine alpha. And I'm solving for cosine of this angle measure, so I need to divide both sides by the negative 451.4. So the cosine of this angle measure A is negative 395.05 divided by negative 451.4. So 0.8751 and some goes on for a while. But now I'm going to do the arc cosine of both sides. And I get 28.9 degrees. Since I don't have any other angle measures to compare the accuracy to, just follow the instructions that you're given in your homework as to how many decimal places to round to. So I'll just use one decimal. That's fine. So 28.9 degrees. Now, let's look back at our triangle. So that is this angle measure. Now, I could certainly repeat that exact same process and figure out what the next angle measure is, but it's generally accepted that the law of sines is a little bit easier. So I'm going to switch and use the law of sines to get the angle measure B. So sine of B divided by 12.2 is equal to the sine of 28.9 divided by 9.8. And I'll grab my calculator to figure out what that is. So, let me clear this. So 12.2 sine of 28.9 degrees divided by 9.8. So that gives me a value that is the sine of angle B. So I'm going to do the arc sine of this number, which will tell me what angle B is actually measured at. So B here is 37.0. All right, and with that, I can now just subtract the two known angles from 180, and that will tell me what angle measure C is. So 180 minus 37.0 minus 28.9, and that gives me 114.1 degrees. Next up, solve the triangle with the following characteristics. All right, side A is 2.4 inches, B is 11.3 inches, and C is 24.5 inches. Now, already, I know that there is no such triangle that would work. And the reason that I know that is because this fails the triangle inequality. The two shorter sides, when added together, is not longer than the third side. So it's going to fail. But let's assume we didn't know that. and we just went ahead and tried to solve for it. So what we would do is take 2.4 squared is equal to 11.3 squared plus 24.5 squared minus 2 times 11.3 times 24.5 times the cosine of the angle opposite the 2.4, which is A in this case. So I'm going to need my calculator. Keeps going from one side to the other here. All right, I will do 2.4 squared minus 11.3 squared minus 24.5 squared. So I have negative 722.18 on the left-hand side of the equation. Then 2 times 11.3 times 24.5. This is going to be negative 553.7 cosine A. Oops. So when I divide the 553.7 over, cosine A is equal to, let's find out, so negative 722.18 over negative 553.7. It's 1.304, goes on for a while. We know that the range of cosine is -1 to +1, so this is outside of the range of cosine, which means when I try to take the arc cosine of this, it's going to result in an error. So there is no such triangle that will work. Let's do an example with some bearings. So a ship leaves port and travels on a bearing of north 75 degrees east for 308 miles, then turns and travels on a bearing of south 63 degrees east for 137 miles. How far away from port is the ship? So try and get a sketch to begin with. We explained how bearings work earlier in the class. You still have access to that bearing applet if you want to kind of refer back to it and see how that goes. But basically, just keep in mind your standard compass. You have north, south, west, and east. So if you're traveling on a bearing of north 75 degrees east, you're moving in a direction kind of like this, as you're 75 degrees toward the easterly direction of north. So here's what I do. I just draw a point and I call that port. All right, and then draw a line and I call that north. So 75 degrees toward the east off of north. I'm going to draw something in. So I'll draw that line in. Now I know that it traveled 308 miles. So I'll call the length of this 308 miles. And this is where the ship changes direction. So now the ship is traveling on a bearing of south 63 degrees east. So if you're south 63 degrees east, you're measuring 63 degrees toward east, but from south. So it's kind of like this. So this would be 63 degrees toward the east, measuring from south. So what I'll do is just again draw a vertical line representing my north-south line, but I'll draw it in the southerly direction. And I'm 63 degrees toward the east from that. And then this ship travels 137 miles, so maybe to right there. Now, the question is asking, what is the distance from port of this ship? So what is this distance right here that I'll put in green? So clearly we have a triangle that we can work with, but we're going to have to figure out some information about that triangle. We know 2 of the side lengths. We want to get the third one, so we're going to at least need to know one of the angle measures contained within, which means I have to work with figuring out what that angle measure is. Because if I knew what that angle measure was, I could add it to the 63 and I would know an angle within this triangle. So what I'm going to have to work with here is a property of geometry that you may have forgotten, but it's a good thing to remember. So north-south lines. All right, I'm going to extend this one. North-south lines are parallel to each other. All right, at least on a small range, they're assumed to be parallel. So when you have a transversal, which is a line that passes through 2 parallel lines, the opposite angles in that are equal to each other. So this line right here, which I'll kind of dash, is my transversal of the 2 parallel north-south lines. And so if this angle measure is 75 degrees, then this angle measure is also 75 degrees because they're opposite angles with respect to a transversal cutting parallel lines. All right, so that means that total angle measure is 75 plus 63, or 139 degrees. Oops, 138, sorry. Okay, now, given that, what we're going to need to do is work with the known angle measure and the known 2 sides, figure out what the length of the third side is. So what I'll do is just say, all right, d squared is equal to 308 squared plus 137 squared minus 2 times 308 times 137 times the cosine of 138 degrees. And I'll get out my calculator and find out what this is. Okay, so let's clear everything out here. All right, 308 squared plus 137 squared minus 2 times 308 times 137 times the cosine of 138 gives me that number, which is very large. However, it's the square of the answer that I want. So this distance then should be approximately 420 miles when you round to the nearest whole number. The last question asks a hypothetical question. What happens if you use the law of cosines in the ambiguous case? So solve the triangle with the following characteristics. I have angle A at 45 degrees, B at 7 meters, and A with 3 meters. So I am not in one of the types of situations where the law of cosines is necessarily applied. Generally, you would use the law of sines in this situation because you know 2 side lengths and the angle opposite one of those sides, not the one in between them. But let's see if we can apply the law of cosines and just see what happens. So for instance, I could say 3 squared is equal to 7 squared plus c squared minus 2 times 7 times c cosine 45 degrees. All right, or let's see. 9 equals 49 plus c squared. 2 times 7 is 14, so minus 14c. The cosine of 45, it was the square root of 2 over 2. We know that. 2 goes into 14 7 times. If I take 49 and move it to the other side, 9 minus 49 is negative 40 equals c squared minus 7 square root of 2 times c. This is the form of a quadratic. So let's set it equal to 0 and bring everything to one side, because that's generally how we go about solving quadratics. And if we solve this quadratic, let's say we use the quadratic formula, for instance. Remember, the quadratic formula, is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Then let's see what happens if we apply this. So we're basically saying c is equal to 7 root 2, because I'm taking the opposite of negative 7 root 2, plus or minus the square root of negative 7 root 2 quantity squared minus 4 times a is 1, c is 40, all over 2 times 1, because a is equal to 1. So 7 square root of 2 plus or minus, if I square 7 root 2, so it would be 49 times 2, which would be 98. So the square root of 98, 4 times 40, 4 times 4 is 16, so minus 160, all over 2. 7 root 2 plus or minus 98 minus 160 should be negative 62, I believe, which means the results of this are complex numbers, and that's an indicator that we have no solutions. So what this is telling me is that there is no such triangle. So recall from the ambiguous case, you could either have 2 triangles that would work, 1 triangle that would work, or you could have no triangles. So this is the case where there would have been no triangle that would have worked. Now, what's interesting is it comes down to a quadratic. And a quadratic can have 2 solutions, 1 solution, or no solutions, depending on the term that's called the discriminant, b squared minus 4ac. So if that term is greater than 0, it means there is 2 solutions to your quadratic. And if there's 2 solutions to this quadratic, that means there are 2 possible triangles that you could end up with. If that is equal to 0, then that means there is 1 solution. So there's only 1 triangle that would work. Or if that is less than 0, then there is no solutions, and therefore there's no such triangle that exists. So effectively, solving the ambiguous case is very similar to the concept of solving quadratics in general. So there's a lot of things in mathematics that tie together once you see the underlying meaning behind it all. So anyhow, that is everything for the law of cosines. Hope you enjoyed it, and see you in the next video.